Hi, folks. Chris McClure. One thing I wanted to start off with has to do with quizzes. Now, some people have asked me about where the quizzes are. Well, the short answer is they're in the My Lab and Mastering website / portal. They used to be embedded into Blackboard, but that technology is not as good as I like it. So I've decided to have your quizzes done with my lab, my stat lab in particular. So go ahead and click your link to the class itself, and then you'll click on quizzes and tests under the homework link. And then when you pull that up, you'll have it right here. This is the one for you to take after you've done all of the Chapter 1 homework. Okay. Now, all these pre-tests and post-tests, those are fun for you to do, but they don't count one way or the other towards your final homework score. So, but I'm not trying to discourage you from taking those. Just understand that they don't count. This is what counts. You'll have 120 minutes to do this quiz. And I should point out that there is a Chapter 1 review homework, and if you notice this flag right here after you, or when you hover your mouse over it, it says that you must do Chapter 1 review quiz before starting this assignment. So the questions that you'll see in the Chapter 1 review homework are based on your performance on the quiz. And I have a feeling that if you score well on the quiz, that you'll have next little or no requirements for this review homework. Okay? And then you move on to Chapter 2 homework. Okay? Now, moving on to the material here in Chapter 2 that I want to go over with you. This is going to be talking about taking that visual depiction of the distribution of your data beyond just histogram. Last week we talked about how a histogram is similar to a bar chart in that the height of the bars are directly related to the frequency for each of the classes in your frequency distribution. We're going to look at other different charts / graphs in this section right here. Excuse my throat, I've developed a bit of a cold over the last several days. So we're going to take a look at some charts that are good and some that are not so good. You'll notice that the good graphs are the ones that are effective in revealing the important characteristics of the data, and that they don't have issues regarding distortion or bad scaling on either of the two axes. You know, they could be technically correct but misleading. So we're going to hopefully point out some things for you to look at in helping you recognize bad graphs and to identify exactly how they are misleading. Now here is one chart that we will use a lot. You probably have already seen this before in a previous course, and it's a scatter plot. Scatter plots are created when you have a set of two variable data. For example, if you wanted to try to discover the relationship between arm circumference and waist circumference, in other words, is there a relationship between how large your arm is and how large your waist is? Well, you can take a bunch of different individuals, and for each individual, make two measurements. One measurement would be a waist circumference, where they wrap a tape measure around someone's waist at the belly button. And then the other measurement is to take that tape measure and wrap it around someone's arm, probably at the bicep. And you can treat the waist circumference as one variable. I mean, and it doesn't really matter if it's going to be the variable on the horizontal to the vertical axis, but you choose one of the two variables. We'll talk more about variables at a later date, but just understand that, hey, waist circumference could be a variable amount, which it is in this case. And then arm circumference on the vertical. Notice the scaling for both the horizontal and vertical axis, that the scaling is appropriate in that the scatter plot fills up most of the chart. Now, if you had a scatter plot that just went from here down to here, just a small portion of the plot, then you would have to think about rescaling your plot. But notice, though, that there is kind of a linear positive trend. And by the way, this is for males. You'd see a different sort of relationship for females. Still, it would be a positive, generally speaking, though. But maybe with a different slope. But you could come up with the equation of a line to model this relationship. We have a separate discussion, though, on what this relationship is called. All right, here's a different sort of graph called time series graph, where one of the variables is going to be a time variable. Here we've got the Dow Jones Industrial Average, high prices over time. It looks like that there was one measurement per year, and that measurement was the Dow Jones Industrial Average high value for that year, and then plot it versus time. This is an example of a time series data chart, time series graph. Notice, by the way, that the dots are connected with line segments, typical for a time series graph. Here's something similar to a stem and leaf plot, in which you could have data, single variable data, by the way, that are scores or some other sort of measurement. Integer values, by the way, integer values. This won't work so well if you have non-integer values, or at least some sort of discrete value, maybe out to the tenths place or hundredths place, as long as it doesn't cover too wide of an interval. But here you got IQ scores for the low lead group. You've seen this data set many times before. What you do here is that you place a dot over its respective position on the real number line. So you can see that there's one reading at 70, one reading at, say, 56 or so, one reading at 50. Over here, it looks like there's 1, 2, 3, 4, 5 readings of 77, I suppose, or 76, whatever that is. Over here, we've got approximately 1, 2, 3, 4, 5, 6, 7 readings of about 96, and so forth. Yeah, that's a dot plot. You don't see it very often. It's a lot less common than they used to be decades ago, but you'll see them crop up once in a while. Here's the old stem plot, aka stem and leaf plot, probably something that you learned back in 7th grade, in which, in this example, you can strip off that last digit, and then the digits to the left of that ones position appear right here. And then you draw a vertical line, and then to the right, you write down the rightmost digits, in this case, the ones digits. And here, the 5 to the left and a 0 and a 6 to the right means that there were 2 readings in the 50s. There was a reading of 50 and another reading of 56. There were no readings apparently in the 60s, Down in the 70s, we had a reading of 70, of 72, 73, 74, and so forth. And by the way, this is pretty darn handy because you don't even have to create a bar chart or histogram or whatever. You can immediately see the distribution of the data. How there's a clump in the 90s, for example, and so therefore the peak is there. The average value is probably in the 90s. The digits in the tens and hundreds positions are said to be the stems, and the digits in the ones position are said to be the leaves. All right, moving along here. Bar graph uses bars or of equal width to show frequencies of categorical or qualitative data. Let me just stomp my foot on that one. Remind you, this is for categorical and qualitative data versus histograms, which are typically for the quantitative data. Bar graphs are for qualitative data. Histograms for quantitative. Vertical scale represents frequencies or relative frequencies. Horizontal scale identifies the different categories of the qualitative data, sizes, colors, etc. And you could have it for one variable. You could even have it for two or three or multiple variables side by side. Here's an example of a two variable bar chart, in which case we have males and females, median income in terms of thousands of dollars. So right here, this is 30,000. Down here is 15,000, 10,000, and so forth. And you see the two different colors of bars. The blue is for males, the pink is for females. And the height of each bar represents the median income for the year 1950 for a male or for female. And oh, by the way, you could see that there's still that disparity in income between males and females as late as 4 years ago. But this is a great way of tracking some measure, in this case median income, over time, or some other variable besides time as well. Here's another example here. This is a chart typically for qualitative data called the Pareto chart, with the bars arranged in descending order according to frequencies. What contributes most to happiness? Well, here are different categories here, and you can immediately spot that family/partners is the most important factor in contributing to happiness, and then it's downhill from there. And that's the way it is with all Pareto charts. It goes from largest to smallest. Vertical axis is almost always going to be a percent. Pie chart goes hand in hand with the bar chart or Pareto chart. You probably have seen these before in a previous class. Let me just remind you that the angle for each sector corresponds to the relative frequency. Look at here. For example, for family/partner, that looks to be about 65%. So if you were to take 65% of 360 degrees, and I'm going to pull out my handy calculator and take 0.65 times 360, that's about 234 degrees. So I would have, if I'm doing this by hand, have used a calculator to find that there's 234 degrees, and then use a protractor to mark off the 180 degrees to get half of it. 234 minus 180 is 54, so I'd mark off another 54 degrees to get this piece of it. And then the angular measurement for these other sectors are likewise a certain, respective percent of 360 degrees. Notice also that each sector is appropriately labeled and has a different color, or if you're dealing with black and white only, maybe a different shade or a different pattern to distinguish the categories from each other. Here's a frequency polygon. Going back to the IQ scores of a low lead group, that same data value, that data set. So if you were to go back to that histogram that we did last week regarding the IQ scores of a low lead group data set, but if we were to connect the top middle of each vertical bar on the histogram and then took away the bars, and we used a sequential line segment to connect the dots, then we would have our frequency polygon. We could even bring in 2 or more variables. Here we have high lead group in the green and the low lead group in the orange, and plot them on the same set of axes, IQ scores versus percent. Notice for this one, the frequency, the absolute frequency, was on the vertical. Over here we have percent. So this allows us to compare distributions of the two data sets. Notice that there's a more marked peak for the high lead group that is probably lower than the average value for the low lead group. Basically, pointing us to at least conclude with a little bit of uncertainty, tentatively conclude that children who were exposed to low lead had a less of a decline in their IQ compared to children who are exposed to high lead group. Not to say that conclusively exposure to high levels of lead causes a decrease in intelligence for children, but at least this is one piece of evidence to show that, or to support that conclusion. Here's an ogive. It shows us the cumulative frequencies. Now take one of these data sets, like the low lead group, and take that frequency polygon, but instead of doing the relative percent for each IQ, imagine that you were to go down the cumulative frequency column of that data set, of that frequency distribution. Well, this line plot is for that cumulative frequency distribution. So you should see the ogive as a chart with the line that is never decreasing in altitude. It's always either level or increasing. Notice here on the left that you have cumulative frequency. This is very well could have been a cumulative relative frequency, as in a percent as well. You'd still have an ogive. Now let's talk about some charts that are deceptive, regardless of whether the author has intended for them to be deceptive. They're still deceptive. Now, I want you to take a look at these two charts. They're really for the same sets of data. Now, if you change the scaling, you can really exaggerate, or on the other side of the coin, you could attempt to do the opposite of exaggerating, kind of more like gloss over differences. Take a look on this vertical axis where it starts 30, ends at 36. When you blow up the scaling like this, actually it's not blowing it up, but it's really zeroing in on the scaling, you really are going to exaggerate the differences in fuel economy for the three vehicles. And honestly though, is 31 all that different than say 34 or 36? When in reality we should be depicting the data chart more like this. Because, when you're in the 30s, that fuel economy is still pretty good. So if you only want to focus on the differences between the three vehicles, then you could show it like this, but that's kind of misleading. It shows that the Toyota Camry really has terrible fuel economy relative to the Chevrolet Aveo, when in reality it's only off by 3 percentage points. Or sorry, 3 miles per gallon. And that there only is about 2 miles per gallon difference between the Honda Civic and the Aveo, which relatively speaking is not all that big of a difference. So this is probably more accurate, less deceptive compared to this one here on the left. Pictographs, got to be careful about using images. Let me go back. Sorry about that. To really spice up your presentation. Having interesting looking images, makes it fun and exciting to look at your graphs. But you got to be careful that you are not creating a false impression that distorts your data. If you double the size of a square, for example, that does not, relate to the your variable increasing by a factor of 2. That really actually goes along with your variable increasing by a factor of 4. And if we're talking about 3-dimensional figures, by a factor of 8. Because 2 cubed is 8. So here's an example. If we want to show how your income increases with your educational level, we could show it like this, where we have a portion of $1. And the length of these imagined rectangles here corresponds to the dollar figure that they're telling us, the average annual income. Bars have the same width itself, not too bad, but it's too busy. It's too difficult to immediately grasp. It's better to have distinct bars. So it looks kind of cool, but it really detracts from what you're trying to portray. Well, you could try this where you have these 3-dimensional blocks, but, let me go ahead and talk about the difference between 74,602 minus 51,206. Then I'm going to divide that by 51,206. And that's about 46%, so 45.7% increase. So this tells you that you could expect about a 45.7% increase in your in your annual income if you go on to achieve an advanced degree beyond a bachelor's degree. I'm talking about master's, PhD, JED, MD, PharmDs, any other sort of professional degree. All lumped in this category. But so if you were to say increase one dimension like the height by 45.7%, well, then you should really do, well, got to be careful. Did you do that the same, for the horizontal dimension and the, that third dimension, the depth dimension? If you did, well, let's take a look here. I'm going to take 1.457 and I'm going to actually cube it. Then what you've done is created a figure that's over a factor of 3 increase in the size, because that's our eyes are picking up this three-dimensional figure. It's more than 3 times the size three-dimensionally compared to this one. All I did was I took 1.457 raised to the third power. So this is kind of a disconnect between this number and this number. This number here, the 74,602, is only 45.7% larger than this number. But this three-dimensional block is over 3 times the size of this three-dimensional block. So, but what you could do, though, is if you still want to do three-dimensional blocks, is just increase only one dimension, like the height, by that factor, 45.7% in this case, and leave the other dimensions alone. Okay? Now, to be safe, just use a nice, simple bar chart like you see here. Make sure that the labels are adequately labeled or described, so it's absolutely clear that this is annual income on the vertical and educational level on the horizontal. And that not only do you have to figure out what the height of each bar is and estimate the the value, you actually have that value right here. You can immediately see that no high school diploma, people who have never finished high school can expect to earn this amount per year. But you could also see that as you go from left to right with higher and higher educational levels, that you can see a steady rise in your expected annual income. So we want a chart that is fair, objective, unencumbered by distracting features. So when you are looking to create a chart to depict your data, it might be worth your while just to use a table instead of a graph. But if you're going to use a graph / chart, again, eliminate or at least minimize or make simple any sort of eye-catching, distracting design features like dollar signs, money bags, etc. All you need to do is open up a USA Today and look on the front cover, USA Today magazine or a newspaper. And somewhere on that front page is some sort of interesting chart. Some are better than others, but a lot of them have the same issue regarding eye-catching and distracting design features. Be careful to not inadvertently or purposely distort your chart by playing with the scaling of your vertical axis. You know, just think back to that picture regarding the miles per gallon for those three different models of vehicles. There's really no reason to call attention to the fact that two models were 3 miles per hour or 3 miles per gallon different from each other, unless you're really trying to trump up the one vehicle over the other vehicle. But in the context of things, 3 miles per gallon, when you're getting over 30 miles per gallon already, isn't really that big of an increase anyway. So better just to let your vertical axis go from 0 to 100%. And lastly, look at this last bullet here. Almost all of the ink in a graph should be used for the data, not for the other design elements. So keep it simple, folks. Make sure that your axes are well labeled with an appropriate tick marks and scaling, and make sure that your chart has an appropriate caption. Okay? So that is pretty much it for chapter 2. And when we come back next time, probably tomorrow, we'll talk about the material in chapter 3. Okay? So that's what we'll do, chapter 3, starting probably tomorrow. Okay, folks. So I'm going to let you go now. Take care, and I'll see you next time.